Working memory acts as the operational system for goal-directed behavior. It is the active retention and real-time manipulation of information required to execute a task. This system is governed by two absolute constraints: a strictly rigid capacity limit and a finite duration for temporary storage. This is the multi-component model proposed by Baddeley and Hitch. For 50 years, it served as the foundational theoretical framework for how we understand these processes. This model successfully categorizes what working memory does across cognitive domains by separating information into distinct abstract buffers. While this framework describes the software of thought, it does not identify the physical, biological hardware that executes these commands. To move past theory, we must observe the physical structures of the brain as they actively synchronize during a task. Deciphering these physical neural mechanisms is necessary to provide a biological anchor for our existing theoretical models. Once we establish a baseline of healthy function, we can begin to measure how biological variables, like aging or disease, interfere with the system. Mapping the precise neuroanatomical breakdown allows us to explain clinical deficits that abstract models alone cannot fully reach. Identifying the complete cortico-subcortical architecture of working memory reveals how pathology dismantles the system, which in turn points towards precise targets for rehabilitation. Psychological models define the conceptual reasons why memory might fail, while a neurobiological map identifies the physical mechanism of that failure in clinical populations. Historically, neuroscientific research has localized the execution of working memory almost exclusively to the cortex. This model highlights the frontal parietal network, the core for information processing. The prefrontal cortex leads, manipulating temporary data. Simultaneously, the cingulate and parietal cortices maintain attention and route information. Success relies on synchronized, oscillating communication between these nodes, organized neural activity. For decades, this cortical loop was considered the complete biological picture of how we hold a thought in mind. However, focusing only on the cortical surface leaves significant gaps in our understanding of how these complex signals are maintained. Modern neurobiology has shifted toward an integrated view. Working memory is not a phenomenon limited to the cortex. High-resolution mapping now requires us to integrate deeper brain structures into the model of active thought. This reveals the midbrain and cerebellum as foundational components of the working memory system. They participate directly in the retention and timing of information, communicating through ascending and descending feedback loops that tether these deep structures directly to the frontoparietal network. Without these vital subcortical loops, the cortical network simply cannot maintain the complex behavioral sequences required for goal-directed action. Successful execution requires a synchronized cortico-subcortical circuit. This is the true baseline of a healthy cognitive state. The efficiency of this circuit is volatile, influenced by a constant stream of biological modulators. Variables like chronological age, shifting emotional states, fluctuating hormone levels, and even daily caffeine intake can shift the network's neurobiological baseline. While these factors cause minor shifts, specific clinical populations face a far more severe breakdown of the circuit. Severe working memory deficits are observed in the elderly facing cognitive decline, youth with major depressive disorder, and patients with traumatic brain injury. Despite having very different causes, these groups often share a nearly identical physiological signature when memory fails. This split screen illustrates structural dysynchronization. On the right, healthy loops fracture into disorganized asynchronous activity. Sometimes this presents as hyperactivation, nodes firing violently to compensate. In contrast, other networks exhibit hypoactivation, where critical nodes fail to register any activity at all. Whether the network is overfiring or failing to fire, the result is the same: the immediate collapse of goal-directed behavior. These neural patterns provide a physical explanation for why tasks requiring mental manipulation become functionally impossible for these patients. Clinical deficits are not an abstract loss of ability. They result from a structurally desynchronized network, one that can no longer support the software of thought. Deciphering these neural mechanisms serves two scientific goals. First, it provides a physical validation for our historical psychological models. By overlaying the Baddeley and Hitch model onto the cortico-subcortical map, we are physically anchoring theoretical concepts like storage buffers to specific, identifiable brain regions. Second, this mapping enables us to reframe clinical treatment for disadvantaged populations. Because working memory deficits are tied to network synchronization, rehabilitation can move past broad cognitive exercises. Clinicians can now identify the specific mechanism of a patient's failure, whether the network is suffering from trauma-induced hypoactivation or depression-driven hyperactivation. Targeting these precise anomalies allows for interventions designed to physically resynchronize the disjointed neural pathways. These programs can now address the impairment from a neurophysiological baseline and a psychological perspective simultaneously. Restoring the cohesiveness between the midbrain, cerebellum, and frontoparietal networks directly restores the patient's capacity for goal-directed behavior. Approaching the brain as an integrated, vulnerable hardware system enables the execution of precise cognitive repair. By mapping working memory from a theoretical construct to a subcortical reality, we bridge the gap between understanding cognitive decline and actively engineering its reversal.